Okay. So today's actual lecture, if I can manage to pull up my notes, is going to be on surface curvature, and I've conveniently started at the end of the lecture instead of the beginning. Okay. Right. So curvature. Ta-da. So remember our discussion of curves on our previous, like a week or two ago. Right, what did we do? We first defined what a curve was and some of the basic things associated with the curve, like its tangent vectors. And then we tried to come up with like scalar measurements we could make about a curve that tell us about its geometry. In particular, we defined curvature and torsion, and then proved that like if I know the curvature of a surface, then or of a curve rather, then I can reconstruct it up to a rigid motion. And we can ask a very similar question about surfaces. In fact, we will. And that's going to lead us to a similar set of notions. But now, like, it's a two-dimensional surface, so you expect at least two numbers instead of one, for example, to reconstruct a shape. Yeah? And indeed, that's the case. We need these two-dimensional functions. The story's going to be a little bit more complicated. We're going to see there's some compatibility conditions to satisfy. These are called the Gauss-Kodazzi-Mainardi equations, I think. But up to technicality, it's a very similar kind of broad picture. So let's get started. Essentially, our goal here is to quantify how much a surface is deviating from being flat, right? Another way of putting that is just we're trying to compute curvature. I'm going to check to make sure the recording is going because my computer's misbehaving. Okay. So we use the term curvature all the time. I think many of you have some intuition just by virtue of my saying the word curvature of what we're trying to measure. But what we're going to see is that actually formalizing that notion requires quite a bit of work and then a lot of careful construction to make sure that we've done all of our calculations properly. Okay? So in particular, our sort of high-level questions are to answer questions like the following. Like mathematically, I look at all these patches and I can qualitatively describe them in different ways, right? Like the ones on the top are sort of elliptic looking, right? They look like eggshells. The ones on the bottom are more hyperbolic or saddle-shaped. The question is, what measurements can we make that actually distinguish between all these different things? Does that make sense? And there are clues that can help us here. Like for instance, if we start drawing little infinitesimal circles on these different objects, we might notice that the ratio of surface area to like arc length starts to change. Like for instance, if I give you a circular piece of string and I push it down on the surface and I look at how much surface area it encloses, we'll see that depending on whether it's a saddle, which has sort of excess surface area, or one of these other shapes, we'll get very different configuration. Actually, I got that backward. I guess these guys have more. Sorry. And here's another one. We can answer is how do surfaces interact with the space around them? So for instance, here we see two different developable surfaces. Remember, that means that we can make them out of a flat material like paper. And somehow this is a different species of curvature that really requires the space around the surface. So if I'm like an ant walking along the surface, I can measure things like surface area and arc length, but I can't distinguish between these two objects, right? So something a little funky is going on here. In fact, we'll see that there's two different notions of curvature we'll need to describe a shape completely. Okay, one of them will measure one effect and one will measure the other. And the sort of high-level question that we'll answer at the very end of this is like, how much does the space surrounding a surface matter versus like, I just have a piece of string and I can walk around the surface locally. Of course, there are many practical applications of the machinery beyond computer science. My favorite one is this cute little article I had a few years ago on the best way to eat a piece of pizza according to science, where they talk about how curvature relates to rigidity. Of course, many of you, I see you in this data center applying this every day. When you pick up the free pizza with the like bugs and mice crawling on it because it's this data center, you kind of curve it a little bit and suddenly it becomes rigid. Notice that the pizza is an approximately flat object and curving it is not like turning it into an eggshell. So somehow that starts to give you some clue as to what species of curvature maybe is associated with different types of bendiness. And indeed, I encourage you to look at this extremely informative article to learn. I think they actually do make a quick attempt at explaining a little differential geometry here, which is cute. It also makes a wildly bad approximation that a piece of pizza is like a rigid, infinitesimally thin thing, which is a piece of pizza that I would probably send back. Okay. From a mathematical perspective, I mean, essentially, we do have some machinery for describing curvature, namely what we develop for curves. And so it makes sense to use that as a starting point, but what we're going to see is it's not obvious how to apply that theory. So for example, like curves have curvature and surfaces have curvature, and they're not quite the same thing. So here's a simple example. The floor is flat, but if I drive my little car around on the surface, I can like turn it around in a circle, and I'm experiencing curvature of a curve, right? I'm bending, but the underlying geometry has no curvature. And we're going to see that we'll do a lot of effort to essentially separate these two things, right? That like there's curvature of a curve by virtue of bending a steering wheel, and then there's curvature which is just due to the fact that my car is driving along some curved object. And that those are two kind of phenomena that we can very easily kind of orthogonalize given the right mathematical framework. Does that make sense? That's the intuition to have in mind. I think it's really easy in these derivations, if you're not used to this kind of thing, to like lose the forest through the trees and just start doing partial derivatives and like indices and things. But these are intuitive objects. Like any of the objects that we defined today, you should step back 10 feet and say like, what is this thing measuring? Like literally measuring, like with a measuring tape. So that's our plan. So let's recall a few notions from our last couple lectures, and then we'll get started. One particularly important object we're going to work with a lot is something called the surface normal. We'll call that little n. This is important. I'm going to repeat that. The surface normal is little n in today's lecture, because we're going to end up with very irritating, clashing terminology where we're going to have a curve along a surface. The curve has a normal, the surface has a normal, and they're not going to be the same. Just keep that example in mind where I'm driving around on a flat plane. So the flat plane has a normal that's just constant and up, but the normal to the curve is probably like in, right? Because it's like where the curve is bending. Does that make sense? Nods, acknowledgements? Cool. All right, and then if we have an orientable surface, we can actually identify a second object called the Gauss map, which is that function which maps the entire surface, every single point, to a unit normal. And if our surface is orientable, which we're going to assume it is today, then this function, it can be thought of as like a smooth object. It doesn't have a jump. So as a quick recall, like what would be an example of a surface where you can't do that? The Mobius strip. Thank you, Matthew. Okay, so right. And then at the very end of a few lectures ago, we defined a particular object called the Frenet frame. And this is sort of the aesthetic that we're going for today, which is this little theorem at the bottom, which is like we make two measurements about a curve, and that's enough to reconstruct the curve. The question is, can we do the same thing for 3D surfaces? Okay. Any questions about our like whirlwind review there before we get started? So good head shake. Good, good. Okay. Right. So here's our Gauss map again. I'm only putting it here just to remind you that this really is an object that we can work with and think of as just a continuous function that we're analyzing. And in particular, we kind of only know how to do one thing in differential geometry. We already have the geometry. We're missing the differential part. And that's essentially, we can compute derivatives of things, right? And remember, like, how do we compute curvature? Like, we took the tangents of the curve, we differentiated, got the normal. Took the normal of the curve, we differentiated again and got, whatever, binormal. And that was what allowed us to understand curvature, was like, how are tangents and normals changing as I move along an object? Right? That's really what we were doing in our curve lecture. So when we talk about measuring curvature of a surface, any predictions? Like what are we going to do? Like what's going to be our construction here? We have an object, little n. Might as well differentiate it, or like kind of understand how the normal is changing as I move along the surface. And obviously, that gives you some clue as to bendiness. So for example, if I have a plane, a flat object, what's the derivative of n? 0. What would I expect the curvature of a plane probably to be? Also 0. Yeah, so there's some superficial connection here. Cool. So in differential geometry, we like slightly different notation than in other areas. We've already encountered this in previous lectures. But remember, we defined this particular object called the differential of a map. Right? So those of you from undergrad calculus are probably used to computing Jacobians, right? This is just a reshaping of Jacobian to think of it as kind of like a function instead of a matrix, right? So this is actually the kind of full definition of a differential, but it follows what we did before. We're going to say that if I have some map, for instance, we did a differential of a function previously, the definition here is identical. By the way, you can think of a function as a map into a one-dimensional manifold, namely the real line, if you want to be fancy. Yeah? So in general, the differential of a map, what we're going to do is we're going to, so we have some map from some space into some other space. We add a point P, like that. So the differential of my map, let's see, what letter did I give it? Phi. In fact, I used the little cute curly phi this time, right? Is going to do the following. So I will take, for a given tangent vector out of P, right? I'll take a curve through my point P, that's supposed to be a P, with tangent V, right? So we have gamma of 0 is equal to P, gamma prime of 0 is equal to V. This is like the initial velocity of our curve gamma, right? And then we defined, just as a little bit of recall, let me grab the eraser here. The differential, which was this object, d phi at P evaluated at V, like that. And we can think of it as phi composed with gamma prime at 0. Right? So in words, what's going on here is like gamma is sliding along the source surface. And if I compose that with phi, then I'm actually drawing some path on the target surface. And so there's this mapping from tangent vectors here to tangent vectors in the image of the map, right? That's all this thing is doing. And in a previous lecture, we already kind of argued that this is independent of our particular choice of gamma so long as it satisfies these two conditions. So this, in other words, this definition is okay to have. Everybody with me so far? Fantastic. So we only have one function to work with on a surface that is sort of canonical to that surface, which is this normal, right? And so essentially, the way we're going to define the curvature is going to be based on taking dn, where n is that Gauss map. Now, usually there's the guy that sits over here and is always asking me these remaining geometry questions. It looks like I scared him away. But his first question would be like, what do I do in that case, right? Because then I don't have a surface normal. Like if my surface isn't embedded, I don't have access to this Gauss map. And my answer to that would be yes. Essentially you have to go to a lot more work to define some of these objects if you're not embedded and can't like talk about the space around your surface like we're doing here. Okay, so essentially with that we can do some calculations, which is fun, I know. So in particular, what we want to do is take dn, where we're thinking of n as this function. And the first question that we want to answer is, what is the target? So dn takes a point on our manifold. We're going to see that dn outputs vectors in a very particular vector space. Okay, so let's do that calculation really fast. So in particular, maybe I'll change it up. I'll draw my other surface. Here's my manifold M, right? And we'll say that I'm at some point P. I have a tangent vector V, and orthogonally to V is the normal vector n, right? That's our picture. So here, you might not believe it from my chalkboard drawing, but the n vector is pointing off of the surface, and the V is in the tangent plane, okay? All right, so we're going to take a curve, gamma, which will map some little tiny interval, right? Because we're only going to be doing derivatives at 0. We don't really have to worry about a long curve. But now, we're going to take the curve to be kind of moving along the surface, like that. Oops, but it's supposed to have tangent V. So more like that. Okay? So in particular, we're going to have gamma of 0 is equal to P, and gamma prime of 0 is equal to V. Okay? For just some tangent vector V. So remember, just by definition of differential, right, what is dn at P of V? Well, I know by definition that it's n composed with gamma prime of 0. Does that make sense? That's just literally plugging into the definition. Okay, so essentially, in the first 10 lectures of this course, we only have that one tiny proposition that we proved a couple of lectures ago about unit vectors, and we're just going to keep applying it over and over again. Notice that n is a unit vector, right? So this composed function is a function from this interval into unit vectors. Yeah? So what does that mean? What is that? What conclusion can I draw about this derivative? Do you remember? Yeah. That's right. This derivative here is orthogonal to n at p, I guess. And the reason is that we showed that this is true anytime you have a function that outputs unit vectors, that its derivative is orthogonal to the function itself. Remember we used that to do curvature, like the curvature normal? Because we took the tangent, we differentiated it, then we argued from this fact that the normal is 90 degrees to the tangent. Exactly the same thing going on here. Cool? Yes?
Some questions. So, is the differential same as like the directional derivative that we take the limit?
It is exactly the directional derivative. It's the directional derivative of n in the v direction. The reason we use this weird definition is we have to be careful that we're only allowed to see the surface. We don't want to use a definition that requires like leaving the surface. Yeah, because this map isn't even defined away from the surface. Yeah. Okay, so dn is orthogonal to the normal vector. What is the space of things orthogonal to the normal vector? We have notation for this. I heard it all over here in a blob on 3. 1, 2, 3. Yeah, it's in the tangent plane, in the tangent space. This is in T_P of my surface. So already we learned one little fun fact. We differentiate the normal vector and we get something tangent. Okay? Right. So we learned a little bit about this function dn. I see it. We're going to give it a name, by the way. If you look in differential geometry books, they call this thing the shape operator, which is a good band name. And essentially, this thing is going to tell us everything we need to know about local geometry. Yes?
So that only works if we're in a three-dimensional ambient space.
That's right. So in general, to have a normal vector, your ambient space needs to be one dimension bigger than the space of your object. Yeah. But curvature in higher dimensions is also a much more complicated object. You'll have to look into the Riemann curvature tensor for that one. Yeah. Any other questions? That's good. You're simulating the missing colleague here. Okay. Fantastic. So we have this object dn. Our suspicion is that this thing has something to do with curvature. We're not quite there yet, but we're close. And we're going to start doing some calculations with this object. In particular, we're going to define one of the most famous objects in differential geometry circa 1850, which is this object called the second fundamental form. And basically, all this object is a different way to kind of reshape the shape operator. One thing that's quite clear in this expression is if I know dn, then I obviously know 2. And a little bit of linear algebra, you can argue if I know 2, I also know dn. I'll let you argue that one at home. But essentially, the second fundamental form is a bilinear thing. It inputs 2 vectors, v and w, and it outputs this very special quantity, minus v dot product dn of w, right? So again, what is this doing? It's like I have the normal vectors, this little unit vector as I move along the surface, and it's saying I'm going to like differentiate it this way, right, like in the w direction, and I'm going to take the dot product of that derivative, which we know is some tangent vector, right? We just showed that. So I'm going to take the component of it in the v direction. That make sense? And like since essentially we know that dn of w is some tangent vector, like we really do have the shape operator, right? By plugging in different v's here, we can kind of like sense it. Remember I kind of suggested that there's this duality that we use a lot. This actually goes all the way back to lecture 2. We talked about like linear operators that kind of, like there's matrices, and sometimes matrices are like things that you multiply with to get vectors, and then sometimes there's matrices that you use to kind of define dot products. Notice that essentially what I've done here is converted from one to the other. Yeah? Nods? Agreement? Cool? This is really exciting? Awesome. Okay, so, and there's a minus sign there just for technicality. We'll see why in a second. I believe just about everybody agrees on that minus. And like the Laplacian operator will define later, like nobody agrees on the sign. And half the time there's research papers that like switch signs halfway because they like start working from someone else's book. This is not the case. This is convention. And I checked this morning in my office. That is correct. Okay, so in particular, I mean, we haven't really figured out what this 2 operator is doing, right? And I'd like to build a little bit of intuition for this thing, right? Oh, I forgot on the slide. There's this phrase, lowering the index. Remember, if you look back at our discussion of Einstein notation, you'll see that's exactly what we did to get from dn to 2, but that's sort of a side remark. But in particular, I'm going to take a tangent of the surface, and I'm going to stick it into the second fundamental form 2 times. And we're going to see that a really nice thing happens. Okay, so by the way, our convention for today, assuming that I remember it, is that we'll use capital letters for things associated with curves, lowercase for things that are associated with surfaces. In this case, t is going to be associated with, like, a curve along the surface whose tangent is t, right? So it's going to be a big T. And you guys are going to catch me every time I make a mistake. Okay. This is so much easier than the last time I taught this class on that godforsaken board with the paint. Like, I can just write things. Okay, so let's say that I take a tangent vector, which is in the tangent plane of M. I apologize for, like, slight overloaded notation. There's a capital T in 2 places. Mea culpa, but hopefully it's clear from context. Like, the big T is going to be a vector. Okay? All right. So basically, every argument we're going to do starts the same way, which is we have a vector. What do you think the next thing I'm going to do with it is? Yeah, I'm going to make a curve that has that vector as its tangent, right? Because that's kind of useful. I'm trying to understand, like, how the surface is bending by virtue of, like, driving little cars along the surface and measuring, like curvature of that thing, right? So again, we'll take gamma of s, which again we only really need in some little interval, into the surface. And we're interested in curvature. And remember that, like, a convenient thing that we did in lecture 3 or 4 was to parameterize by arc length, like that. And notice that this is kosher, right? Because I could take any curve with tangent t and reparameterize it with arc length, and the tangent would stay t, because t we'll say is a unit vector. Okay? So maybe we'll add that condition. Okay. With me so far? So I have what's our picture? Well, we keep drawing the same picture. In fact, it's exactly the picture up there. Okay. So, right. So we're going to have 2 conditions on gamma, with gamma of 0 is equal to our point, and gamma prime of 0 is equal to our tangent. Okay. So notice, by definition, this vector t, and in fact, actually more generally, not just t, but every single gamma prime for any choice of s. So this is the tangent to the curve, and the curve is moving along the surface, right? So in particular, we know that it is in the tangent plane to the surface at gamma of s. This notation makes sense. I have this curve that's driving along the surface. And actually, if you recall, this was the definition of the tangent plane, was the set of all curved tangents. Was that a hand or just a? Okay, cool. Okay, so in particular, remember we only have that one theorem to apply, which is how to differentiate things whose dot product is 1 and 0. So because it's in the tangent plane, what's a different way of notating that? You got it. Dot product with what is 0? The normal. Thanks, team. So 0 is equal to the dot product between gamma prime of s, and we have to be a little careful with our notation, n of gamma of s. Cool? Okay. And this is true for all s in that little interval, right? Okay, so what am I going to do with this object? Well, I already told you, actually, right? We just take d over ds of this expression here. Okay? So in particular, oh, sorry, spoiler alert. The derivative of 0 is 0. Okay, sorry, I did that myself. And now we're going to apply the product rule. So remember that gamma prime of s is actually like the unit tangent of s, right? So if I do the product rule, I have to differentiate this with respect to x, dot product with n. What is the derivative of t? Quick review. Almost. No minus. So kappa is a scalar. So put the past two wrong answers together and we get kappa n. That's right. It's the curvature normal of the curve, right? So we're going to say curvature of the curve n of s dot product with little normal gamma of s. Notice why we need big and small letters here, because these are two different normals. Okay, plus, again, we have the curve tangent dot product with, well, what are we doing? We're now differentiating the normal. Do you see that? In a particular direction, which is the t direction, right? So we can actually notate this as dn at gamma of s evaluated at gamma prime of s. Does that make sense? Again, I'm differentiating the normal. What direction am I differentiating again? Well, I'm moving it along gamma, so the direction would be gamma prime. That makes sense? I know this expression is a little tough to digest, so we should think for a second. Cool. So, what is this thing? Let me give you a hint. Thank you, Artemis. This is the second fundamental form. Namely, this is minus the second fundamental form evaluated at t comma t. Just by definition. Okay? So let's rearrange this expression a little bit. And what have we shown? We show that the second fundamental form evaluated at t comma t is equal to the curvature normal of the curve dot product with the normal to the surface. Cool? Yeah? This is exciting. Let's think about this intuitively for a second. So what is this object? This is I'm driving in a car along the surface. My car is driving with unit speed, right? I've parametrized by arc length. And this is the force that I'm experiencing as a passenger in that car. And that force has two components. One component is tangential to the surface, and the other component is normal to the surface. So this is the component that's normal to the surface. Think about driving over a hill, right? So I drive over the hill, I'm experiencing force just by virtue of the hill having curvature, which is different from the tangential force, which would be me turning the steering wheel. Yes? Yeah, yes, yeah. Yeah, you.
Yeah, so could it normally be if this is the normal to the curve, could it be in the plane though?
It could.
Turning the car.
Yeah, yeah. So let's think that's a fantastic question. So the question was what about the planar case, right? So let's say my car is doing donuts in the plane. I'm circling around, right? So my car has no knowledge, in fact, of being in 3D. It's like a 2D object, right? So the curvature, the curvature normal of the thing driving in the plane is going to be in the plane, right? Notice that its component in the normal direction is 0. That makes perfect sense because the surface has no curvature. Yeah? Yeah, sneaky, huh? Okay. So to kind of repeat, essentially, if I'm driving along a surface in my car, right? So I've got my little donut here. I've got my car, and it's following some totally crazy path. Essentially, what we've done in the last couple of lectures is if I'm a passenger in this car, I'm experiencing many different forces, right? One of them is just by virtue of jamming on the accelerator, I'm pulling back in my seat, that kind of force. And how do we correct for that? Yeah, we parameterize by arc length. So we no longer accelerate along the curve, right? So that would be curvature in the tangent direction, which just is not a thing, right? But there's still two additional components. One is I could turn the steering wheel, my car does a big turn like that, and I feel like I'm going to throw out of the car, right? And then a second one would be I'm just driving in a boring straight line along the surface, but the surface itself is changing. Think about driving down a hill. You experience that weird kind of feeling in your car sometimes. So those two pieces, one of them is going to be the curvature of the curve, and the other is going to be the curvature of the surface. Okay? Isn't that cool? This is a very tidy explanation of what's going on with the second fundamental form. Incidentally, so what we essentially argued is that second fundamental form is in some sense acceleration due to geometry is a kind of a cute way to phrase it. You could ask what about the other component, everything that's left? That has a name that's called geodesic curvature, and it's all the curvature that a curve experiences that has nothing to do with the shape of the surface, right? So obviously, if you know these two quantities, you can get the full curvature out of that. That make sense? By the way, this expression, it looks like I just kind of invented it, but it's actually very straightforward. Remember that like the curvature direction of the curve, what do we know? It's actually perpendicular to the, it's like essentially it's in the normal direction of the curve. So it's perpendicular to two things, the surface normal and the tangent to the curve. So that's why this thing, this cross product is essentially the third direction that's left, and that's why you get this value here. It took me a long time to realize that. For a long time I thought this was just like a weird definition, and finally I realized like, no, actually it makes perfect sense. Okay, right, so, sorry, I've got my notes upside down. Now we're gonna do one more calculation which is gonna be convenient for us in this class, and is the one calculation in this course that I've never managed to draw a nice picture of. And we're gonna do it the most shameful fashion possible, which is to use coordinates. And so here's my challenge to you guys. It's gonna be you go home and think about it and tell me how I should visualize this little theorem other than pushing symbols around, okay? But it is just a useful fact, namely that the second fundamental form is symmetric. Notice that that's not obvious from our definition, right? So if we go back to our definition of the second fundamental form, it somehow feels like V and W serve very different roles in this expression. But what we'll see is we can swap V and W and get the same value. Okay? Oops. Okay. So let's do the calculation. And it's going to basically boil down to equality of mixed partials, which is also a fact that I struggle to illustrate. Okay. So, we're going to argue this in the most straightforward and least intuitive fashion possible. Namely, we're going to use a parametrization. So let's say I have my surface. Its name is M, and I've got a map, we'll call it phi, into the surface like that. And we're going to have two coordinates, x1 and x2. Okay? And so we're going to look at maybe a point P, and we know that such a parametrization exists around every point, right? That's the definition of a surface, in fact. Okay? Everybody with me so far? Whew. So, there's a lot of different facts that we can derive, but there's two that are very straightforward. So let's say that I have d phi dx1, right? So remember that my map phi is the parametrization. So this is like the derivative in one of those directions. So it's going to look like a vector over here. And where does that vector point? What do we know about this vector? Well, we know that it's tangent to the surface, right? Because this is a local parametrization. So the sort of derivative of the map into that gives me the tangent plane. Right? So in particular, you know that the dot product of that with n, which I can also, by the way, I can think of n as also being a map from the plane here. Does that make sense? That this is equal to 0, identically. Make sense? And similarly, I could do that in the other direction, right? I could do d phi dx2 dot n is equal to 0. Okay? So, given what we've done so far in this class, what do you think we're going to do to these expressions? We see a dot product is identically 0. We only know how to do one thing. Take its derivative, right? And we also kind of know that because we know that in this lecture we're kind of interested in the derivative of n, right? Okay, so in particular, this leads us to two facts, right? One, let's take the first one and take it in the x2 direction, okay? So in other words, 0 is d over dx2 of d phi dx1 dot n, like that, okay? And we can do the product rule, and what we'll get is dn dx2 dot product d phi dx1 plus n dot product d squared phi dx1 dx2. Right, this is product rule. By the way, remember that mixed partials are equal, so the ordering of x1 and x2 here doesn't matter. Sorry, this is the yucky math part of our lecture today. It gets too little. And similarly, I can take the second guy, and I can differentiate this one with respect to x1. Okay? Sorry, I'm left-handed. I'm going to step in front of this for just a second. So this is d over dx1 of d phi dx2 dot n. And after the product rule, this is dn dx1 dot d phi dx2 plus n, but actually an identical term. Everybody with me so far? What do we notice? These are the same, right? So what is this screaming out for us to do? I didn't hear Matt, but I'm going to assume that what he told me was to subtract these two expressions, and he's right. Okay? So what do I do when these terms go away? What I get is 0 is equal to this one minus that one. That make sense? Fantastic. So in particular, let's give these things some names. We're going to call d phi dx2, we'll call that like tangent number 2. Maybe d phi dx1, like this guy, call that one t1. Okay? So in particular, or I should label it maybe t1, like that, right? Notice this is the derivative of the normal in the x2 direction, dot product with the x1 direction, and then vice versa. So in particular, what we've shown is the following, that the second fundamental form in t1, t2 is equal to the second fundamental form t2, t1. Right? And I got that by subtracting these two things, so these terms went away, and then that's exactly what's left. Right? Because remember, the second fundamental form is derivative of one guy in the other one's direction, up to sign. Cool? That argument went a little fast. I'm being a little sloppy. Am I done? Have I shown what's on the board here? Yeah, the answer is no. I've shown what's on the board for two particular vectors, t1 and t2, but I haven't shown it for any vector. Yeah? Okay. Notice that this is also obviously true. Like if I put in t1 twice, right, then swapping it doesn't do anything. Yeah? So really what we've shown in some sense is ti, tj is equal to the second fundamental form of tj, ti for all I and j in 1 to 2, but really that's only because this is the only interesting one and the other are not doing anything. Yeah? Okay. So now we're almost there, but we're not quite there. One thing that's easy to check that I'll let you check at home is that the second fundamental form is bilinear, meaning it's kind of linear in both of its inputs. You can kind of eyeball that from the definition. So what does that allow us to do? Well, now let's take any v and any w. Sorry, this board is like drifting upward for some reason. Okay, so now we're going to take v and w, which are just arbitrary, in the tangent plane at p to m. Okay? And now here's an interesting thing. We have these two vectors, t1 and t2, that we defined upstairs, right? And those two vectors, actually by definition of surface, they can't be the same vector, right? Because remember the Jacobian had to be full rank. So in particular, they form a basis, right? So what can I do? I can write v in that basis, and in particular, I can write it. Do we want to use Einstein notation just for fun? Yeah, let's do that. So let's write it as v upper I, t lower I. We'll see if I manage to get myself confused. Remember, in this notation, I see the same index twice, so there's implicitly a sum here over I. Okay? And similarly, I can write w in the same basis. We're going to say w upper I, or maybe j, t lower j. With me so far? Okay. So now, presto changeo, we can just we can prove our little theorem here. Okay? So in particular, second fundamental form, start on the left-hand side of vw. Well, that's the second fundamental form of v upper I, t lower I, w upper j, t lower j, summed appropriately. I hate this notation. Okay? And remember that second fundamental form is bilinear, right? So in particular, I can pull these coefficients out, right? So this is equal to v upper I W upper j, second fundamental form of t lower I, t lower j, like that. Does that make sense? Well, now we're in good shape because on the previous board, we did show the symmetry property specifically for the t's, right? So now, of course, this is equal to V I W J, second fundamental form, T J T I, right? This is applying the fact up here. And now if I just run this whole argument in reverse, then what I get is 2 of WV. Okay? Isn't that cool? This proof is useless. I mean, like, I didn't use any geometry at all here. I just did, like, boring calculation. It's, like, totally not enlightening, but it's an important fact to check. So what I would encourage you guys to think about at home, there's some, like, kind of philosophical thing going on here, right? I have this surface, and somehow I can, like, differentiate the normal this way and take its component that way. Or I can differentiate the normal that way and take its component this way. And those two things have to be the same, right? That's essentially what we just showed. That's not an intuitive fact to me. It's like something that requires a little thinking. But it's super handy because now we know that we can think of two kind of like a symmetric matrix. And symmetric matrices are really useful. In particular, if you recall, there is something called the spectral theorem for symmetric matrices. And what does that tell us about life? I warned you that this class is going to use all of linear algebra. A symmetric matrix says, sorry. That's right, a symmetric matrix. So in particular, this is kind of like a 2 by 2 symmetric matrix. So it has 2 eigenvectors and 2 eigenvalues. And moreover, those eigenvectors are orthogonal to each other, right? So that's essentially the fact that we're going to use here. We haven't called it out as such yet, but we will. Okay? Isn't that cool? We now like reduced this whole fancy geometric picture to like college linear algebra. Like we just have a 2 by 2 symmetric matrix. Yeah.
Is 2 like a Hessian matrix?
No. It is sort of a second derivative in the sense that, well, no, I wouldn't think of it like a Hessian necessarily. Maybe if you took your surface and you like thought of it as a height function, there's probably some formula that is related to that because you can think of tangent vectors as sort of a first derivative. The cross product of those, so it's like kind of still a first derivative. So the unit normal is like 1. So then if you took a second one, you get something kind of like this. But I wouldn't call it a Hessian just by itself. Like there's probably exists a formula out there with a Hessian in it, but you have to be careful because again, with things like parametrizing by arc length are hard to do if you have a function like this in general. But it's a reasonable question to ask. Like there is a connection there. If you put me at gunpoint on Wikipedia and asked me to find the relevant article, I would look for like the curvature of a graph of a function over the plane. That would be my best guess. You can give me $5 if I'm right. All right. Any other questions? You guys are like not nearly excited enough. We just did a cool calculation. We derived this object. We can differentiate normals every which way, and they tell us all kinds of cool stuff about life. This is exciting and cool and interesting. Darn it. Okay, so in particular, we're going to define two objects that are super useful, and these are called the principal curvatures and the principal directions. And these are sitting at every point along a surface. And this is a thing that people in geometry processing compute all the time. Our next lecture will focus all on algorithms for computing this object. Okay? So here, in particular, is what we're going to do. Sorry, I'm glancing at my notes. How do I want to do this? Yeah, okay. So let's say I'm sitting at a point on a surface. Is it okay if I erase here? We're good? Okay. So we have that nice formula for differentiating, like doing, taking the second fundamental form and evaluating it twice in the same tangent direction. Remember that gave us like curvature due to geometry. That was the phrase we used, or acceleration due to geometry. Okay? So here's a kind of neat thing that we can do. Let's say that we take E1 and E2 to be an orthonormal basis for the tangent plane at a given point P. So it doesn't really matter what the basis is. It's just a perpendicular pair like that. Okay? And then I can define an arbitrary unit vector in the tangent plane, v theta, by just writing the following. I can write, this is just E1 of cosine theta plus E2 of sine theta, like that. So what is this doing? This is like tracing a little clock face, right? Like I've got these two perpendicular directions, and I choose theta. As theta changes around, I'm like pointing in different directions along the surface, right? That's the way I think about this function. Okay? So one thing I can do is I can define kappa sub theta to be the second fundamental form evaluated in v theta, like that. So now I draw this little arrow like this, and essentially as I do that, I measure curvature in each of those directions. Does that make sense? Okay, so when I do that, I can ask a totally reasonable optimization question, which is what direction is curvature the biggest and what direction is curvature the smallest? Right, so think about like standing right at the corner of a cliff, right? Obviously, as I walk in the cliff direction, the curvature is quite large. As I walk along the cliff, curvature is 0. Yeah? So we're going to give those directions names. We're going to call them, we'll call the curvatures kappa min and kappa max, and the directions that they live in are probably v min and v max, or something like that. That makes sense? So one thing that we can show, I think we may skip here. Do I want to skip it? I can't decide. Yeah, well, we can think about it a little bit. So we got a minute. Notice that we can apply bilinearity one more time, right? So let's say that I look at kappa sub theta. Then essentially what we can do is the following. We can say, okay, that's the second fundamental form, evaluating at v theta, like that. We have a formula for v theta, right? Okay, so, well, essentially what we can do is the following. We can say, okay, so once we do bilinearity, essentially what we really need is, we can think of it as v theta transpose times the matrix L times v theta, where Lij is equal to the second fundamental form evaluated at Ei, Ej. And this is just by bilinearity, right? So I take v theta, this little formula here, and I drop it in there, right? And then I pull the sum out of 2, which we know we can do. And then the Lij's here are sort of the 4 numbers that we actually need to know, right? And then they get multiplied by the different basis vectors here. Does that make sense? Whew. So in this expression, suddenly life is starting to look very good, because what is the length of the vector v here, just by definition, kind of? 1, right? So really, if we want the maximum curvature direction, we're solving maximize v theta. We'll get rid of the theta now. V transpose LV, subject to mod v equals 1, right? So in other words, oh, and I guess v is in the tangent plane, like that, right? So like over all the unit vectors, I want to maximize this particular quadratic form. And if you work through the Lagrange multiplier condition, which I encourage you to do at home, if this is not like a turn the crank thing for you, that's great. You really should do it at home, okay? What you're going to show is LV equals LV. Namely, the principal directions are just eigenvectors of this 2x2 matrix. Cool? Moreover, if you plug in then our formula for v theta, you'll get this cute expression for directional curvature that it's actually this is not something you really have to check, it's just like a fun fact. That, it's like the kappa min cosine squared plus kappa max sine squared. Okay. Now, this is somehow a very profound fact about life. Like somehow when I'm saying at a point, I've got this dn object that's telling me how the normal's changing as I like point my face in different directions. And that feels like a very complicated function, right? Like, think about, I don't know, what are those things called that like Shakespeare wears, the little ruffled collar scenario? I think it's called a ruffled collar. So think about like right at the center of that, right? Like somehow, well, either the surface isn't smooth, there's a singular point, but if I somehow manage to smooth it out, I would feel like there's curvature wiggling at a very high frequency as I move around that point. But at least for this notion of curvature, we've derived that just can't happen. If we know two numbers, we know everything, right? And moreover, they have to occur in orthogonal directions. We know that because they're eigenvectors of a symmetric matrix. This really blew my mind in like college when I first encountered this formula. Like you start drawing pictures like, well, what if I have a cliff and the cliff has a curve like that? So like, you know, the edge of the cliff is somehow bending. So I feel like they shouldn't be in orthogonal directions. And the more pictures you draw, the more you convince yourself. Like, no, if I take my magnifying glass close enough to the surface, they're still perpendicular, the min and max curvature directions. It's really kind of a strange fact about life. There are all kinds of pictures you can draw to illustrate such a thing. So as a few examples, for instance, if I have a cylinder, where do we think the principal directions would probably be? So yeah, so one of them is going to be like that, the other is like that, right? Incidentally, remember that eigenvectors are only known up to sign, and indeed the principal directions are also only known up to sign. You can check if you add 180 to theta, this value doesn't change, right? Because it's squared. So more generally, so here's a nice picture from my colleague Keenan at CMU. So here is a nice surface. Remember that we had this phrase for curvature, right? The osculating circle. What does osculating mean? Kissing. Isn't that cute? So we can do something similar here, but now we have, you know, like if I'm standing at a point on a surface, I can like touch a circle to it in many different ways by aligning this you know, like putting the circle in the plane, which includes the normal, and then rotating that about the normal direction. And as I do that, I get different kind of cross sections of the surface, each one of which has a different circle that kind of kisses that curve. And so another kind of picture for the principal curvature value, if you take 1 over that, is just like the biggest possible and the smallest possible radius of a circle that just touches at P as I rotate around. Does that picture make sense? Almost done for today. We've managed to squeeze it all in. We need 1 or 2 final notions. Yes? Yeah? Yeah, you.
I was wondering if we like interpret the equation as like trying to deform like a uniform sphere, a circle, so you get to like an ellipse or something.
Mm-hmm.
Is there some like physical interpretation of this? Like, can I cut out like halves of paper and start to stick it on the surface and somehow?
That's a reasonable question. I think you need to, I don't know, you probably need something called the exponential map, which is like the closest you can get to wrapping a piece of paper around a surface. I'd have to think about it. That map that you've talked about that's deforming the ellipse, that has a name. It's called the Weingarten map. This would be like kind of like the quadratic, like this function here, like restricted to a circle. And old school differential geometry books contain all kinds of pictures of these kinds of things. These days it's just like a passing calculation to a more fancy thing, but it is like mathematicians in the early 19th century were like really focused on these objects and like have all kinds of beautiful intuition. Like these old math books are just gorgeous to look at. They're like these carefully drawn inset figures and so on. Yeah.
On the previous slide, you had this expression for kappa theta.
Mm-hmm.
But it seems like this should not depend on which basis you chose.
Oh, it definitely does, because what's going to happen is otherwise, remember that we plugged in here?
Yeah.
And you have cross terms, right? So there's like the E1, 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 E2, and then E2, E2. And essentially what we're using here is specifically in the eigenvector direction, the cross term is going to vanish. There's a little more work to be done to justify this formula.
Right.
Yeah.
Right, so is this theta with respect to like an arbitrary?
No, I'm sorry. Yeah, that's a good question. This is respect to V min. Yeah. Does that make sense? Theta is 0. Yeah, V min. and you can check that. Like in particular, if you, this is a great question. I'm sorry, I skipped that. If you plug in theta equals 0, notice you get kappa min, right? So yeah. Good question. Sorry, that's my fault. This is really just an eigenvector formula. That's all that's going on here. Essentially, eigenvectors are 2x2 matrices. There are lots of ways to interpret. This is one. Okay. Almost done. Now, one thing that we often do, so we have this 2x2 symmetric matrix. It's well behaved. There are a lot of different numbers we might compute related to this matrix. And there are 2 very famous ones. These have a name. They're called K and H. And these stand for, K stands for Gaussian, of course, Gaussian curvature. Unfortunately, now we're breaking our notation a tiny bit. So these are capital letters by convention. Sorry, we got this far, but now we're done. Actually, we're done with curves anyway, so it's sort of okay. Gaussian curvature is the product of the principal curvatures. Or you can think of it as like the determinant of that 2 by 2 matrix. And then similarly, mean curvature is the average, which is roughly the trace up to a factor of 1/2. Yeah? One thing you might remember from two-dimensional geometry is like up to kind of rotation, these two numbers basically tell you everything you need to know about a 2 by 2 matrix, right? It's kind of like, you know, eccentricity and shearing or something like that. And these are super, super famous numbers, and they are the objects that are the main objects of study in classical differential geometry of surfaces, because they tell you all you need to know about geometry. Oops, I gave it away. And they can be interpreted a lot of different ways. So I've included some other folks' kind of illustration of different sort of principal curvature values and what they tell you about a shape. So the one that I think is easier to think about is the Gaussian curvature. Now the Gaussian curvature, let's say that it's positive. Remember, it's the product of two things. So if I have a positive number, that's the product of two things. What do I know about those two things? They have the same sign, that's right. So what does that tell me about my surface? It means that the minimum curvature direction and the maximum curvature direction both have the same size curvature. Like they both kind of curve down or they curve up. So what does my surface look like at that point? You're pointing at this slide. You're supposed to think critically. Yeah, it doesn't look like a saddle. It looks like a bowl shape, right? And conversely, if I have negative Gaussian curvature, right? So then one of my directions is negative and one's positive, so it like kind of bends down that way and up this way, right? Then I have a saddle-shaped surface. That makes sense? Mean curvature is a little trickier to think about. There's a lot of formulas for mean curvature out there. It's tricky because it actually depends on the orientation of your normal in a sense. Here's a formula that I like. I forget if this year in your homework I added that you should prove it. No? Well, you should. Yet another formula for principal curvature is actually like a direct corollary of that little cosine squared sine squared formula. It's just like high school integrals to work that out. Is that it really is mean curvature in the sense on the right-hand side. Like if I took that directional curvature and I just averaged it over all possible thetas, then I really would get this quantity h. H is tricky because, like, for instance, let's say I have really big positive curvature in one direction and equally big negative curvature in the other, right? It's like a very saddle-shaped surface. Then what do I know about my mean curvature? 0, right? And in fact, mean curvature 0 surfaces are really important in the theory of differential geometry. These are called minimal surfaces. At least it's one sort of definition of minimal surface. And we'll see that it has to do with minimizing surface area. So like if I take the first variation of surface area, which is a calculation I'd love to do in this class, but we just don't have enough time. I actually posted a YouTube video that calculates it on the board. I can send you guys the link if you like. What you'll see is that it's the mean curvature weighted surface normal. So in other words, if I take the surface and I want to know like what direction should I perturb the surface to decrease or increase surface area the most, what I should do is take the surface normal, which kind of makes sense, right? Because you kind of want to bow the surface inward, and weight that by the mean curvature, right? So when mean curvature is 0, that means that like there's no local variation I can make to the surface to improve the surface area. And notice that that's already kind of an interesting fact, right? Because it means that essentially all these saddle-shaped surfaces like locally minimize the surface area, right? Which explains why, like, if you make a bubble with a weirdly curved wire as the boundary, the bubble makes this potato chip shape, right? Okay, and then as we talked about, Gaussian curvature is the sort of more easily thought about object, and it's like distinguishing between saddles, parabolic objects, and elliptic objects. Yeah. There's so many formulas out there for Gauss and mean curvature. If you were a mathematician in like the 1880s or so, like you could make like a full-time business out of just deriving cute formulas for curvature. If you took an undergrad differential geometry class, you would just do this for weeks. I mean, there are all kinds of nice ones out there. You should scroll down the Wikipedia page. Here's one that I kind of like. So for instance, for Gaussian curvature, you can look at like ratios between areas of circles and circumference of circles drawn along the surface and take a limit as the radius goes to 0. And you'll show that like as long as you do your dimensional analysis, right, because you don't want the limit to like explode, you'll get something that tells you about at least Gaussian curvature in this case. That makes sense, right, because we kind of mumbled a little bit. The Gaussian curvature is going to be the thing that an ant can measure. Remember that ants can measure lengths and areas, but they can't measure how the normal is moving. And so this formula is kind of making that clear, although I believe historically it came a lot later. One final note here. The question you should ask, similar to our lectures on curves, right? What did we show? We showed that if we know the curvature or the torsion of a curve, then we can reconstruct it. You could ask the same question here, right? Like if I have, you have to be careful how you pose it now. But in particular, let's say that I'm on the plane, and at every point on the plane, I give you h and k of some unknown map phi into the surface, right? And the question is, can you reconstruct phi, right? You need a little bit more information than that. You need the second fundamental form, right? So maybe instead of these, we give you that, which is slightly easier to work with. And it turns out you need a second object, which is the first fundamental form as well. Notice we did a weird thing. We talked about the second fundamental form, but I never told you the first one. And that's actually a much simpler map. That just says given two tangent vectors, I put them over here, and then I compute their dot product, right? So instead of dn of v dot product with w, it's just v dot product with w. And the short answer here, I see your hand, is that given these two matrices, these 2x2 matrices per point, I can reconstruct the surface. This is an existence uniqueness result. However, what's different from curves is if I knew that there was a map phi and I just forgot phi, I could reconstruct it from these two things. What is not true is that an arbitrary pair of 1 and 2 defines a surface. Like there's certain conditions on these two matrices called compatibility conditions that you need to satisfy. Yes?
So is the first fundamental form the same as the Riemannian metric?
Yes.
Okay.
Mm-hmm.
Do we need to know non-diagonal elements of this matrices for this theorem?
Yes.
So we actually like need them across.
Yeah, you need the cross term and the diagonal one. So that's why h and k are not quite enough. You do need the whole matrix. Yeah. And that's because surfaces have intrinsic and extrinsic pieces. Like this is, you're really trying to reconstruct a shape here. Okay, so that pretty much concludes our discussion. I mean, essentially what that tells us at the end of the day, curvature still determines local surface geometry, but the converse isn't necessarily true. I can't like design a surface by painting curvature on the plane, although there's a lot of algorithms that try to do that in like a least square sense, right? But there's a little bit of work hiding there. Whew. So my apologies for rushing. We actually did like 1.5 lectures today. Next time, just following the same pattern we have in this course, we'll do this whole picture, but now on a triangulated surface, and we'll find that it's really messy. But there's certain other notions, so certain notions of curvature, like Gauss curvature, we can measure directly, which are going to be quite clean. Okay. So with that, have a lovely whatever it is, Tuesday, and I will see you on Thursday.